Ready? Yeah. All right. Thanks for having me, everyone. My name is Kofi, and the slides are already online if you prefer to look at your laptop rather than the screen. My website is kofi.sexy, bottom right, and I am excited to be here because a lot of what I learned about how I think about programming is because of A-Flight and because of some folks in this room in particular, which is fun. So it's particularly terrifying, so thanks for share. So the story starts in 2016, and that was when I was working at A-Flight. I looked like this. Wild. Where'd it come from? My scalp. The hair came from my scalp. And I thought to myself that I will make a programming language, and that it wouldn't be too tricky. And I didn't end up making that language, but I did mess around a lot with compilers. And more and more I found myself asking, what even is this thing I was trying to build? Essentially, what is a programming language? What parts of the build system define the language in particular? And I started to look at code, which I recommend. Code is good. And in particular, I spent a lot of time looking at the Elm compiler, which I think is a really well-organized project. And kind of as an aside, if anyone's interested in learning more about compiler architecture, written in Haskell, but it doesn't use really many of the tricky features in Haskell. And so I actually learned Haskell by way of reading the code for the Elm compiler. And one thing that struck me about Elm as I got to know it better is that I found myself continuing to say that it's a really small language. And I'm going to explain that using the example of inside the compiler source code, there's this data type called expression. This is how you would write a data type in Haskell, data, name of the type. And there are different ways to construct an expression. And the first way in the compiler is you can have a character, which is represented internally as a string. You can have a string in the language Elm, which is represented in the compiler as a string also. And then you have a whole bunch of other types as well, like ints, floats, bars, stuff you'd expect to use in a language, but they're kind of all enumerated here in this expression type. And in Elm, there are 22 of these top-level expression types in total. And so Elm is a language for programming front ends. So the natural comparison a lot of times is JavaScript, and there's a Haskell package for parsing JavaScript, which is what I use to count this expression number in JavaScript. And the thing to remember, even though there are 21 expressions in JavaScript, JavaScript also has statements. And so Elm is just expressions all the way up, whereas JavaScript also has statements where statements can contain other statements. Statements generally contain expressions, but expressions don't typically contain statements unless they're function expressions, in which case they can contain statements. And so this is also the version of JavaScript that was released in 1772. It's called ES3. And it's a cheap shot of comparing JavaScript by just looking at its statement count and expression count. But I think that a lot of folks would agree that JavaScript tends to have multiple ways of expressing or stating the same idea. Actually, in preparing for this talk, I was just trying to figure out how many different ways you can define a function in JavaScript. And does anyone know the number of language constructs that you can use to define a function in JavaScript? Yes?
5.
5. 6. I found 6. Apparently, you can use the function constructor and pass in string literals as the body of your function. All right. So the Elm compiler, the process of compiling is Elm decides how these 22 expressions in Elm map to the expressions and statements that JavaScript affords. So that transition area, what I'm representing with the blue arrow, is what we're going to kind of be thinking about when we're talking about what the programming language is. I'm kind of calling it this mapping between whatever the language decides to define as its own surface area, its own expressions, and how it interacts with the target language. So in Elm's case, generally, Elm has fewer expressions. JavaScript has more ways to have expressions and statements. And so when I say that I really enjoy that Elm is a small language, I really enjoy that the world of programming constructs in Elm is smaller than the world of programming constructs in JavaScript. And Elm, the Elm compiler, takes that world that is Elm and maps it onto the world of JavaScript. Another compiler slash way to write programming languages that I've been digging into is around the Erlang VM. So Erlang is, in my opinion, another example of a really small language. It's got syntax that is not too similar to many mainstream programming languages, but overall the syntax surface area is very small. And Elixir, on the other hand, has a lot of concepts in comparison to Erlang. And this is interesting because it's the opposite than the Elm and JavaScript relationship, because Elixir has a larger surface area. And in particular, the thing that makes Elixir surface area so big is that Elixir supports macros, which is you can write Elixir code that generates more Elixir code at compile time. And that is an ergonomic benefit. It takes some of that from Ruby, and it means that you can write constructs in the language. You can write constructs into the language with your Elixir code. And so that feature is pretty core to the implementation of Elixir standard libraries and the Phoenix web framework in particular. And it allows a bunch of ergonomics that people didn't find in Erlang. And so I actually like to ask Elixir fans pretty often why they don't just use Erlang. And the answer I hear is the ergonomics, that Elixir feels a little bit easier to use, and then also Phoenix, the web framework, because Phoenix is really easy to use. So I like to just say that they're both ergonomics. And so this is my visualization that I made in Google Slides for how programming languages work. So bear with. The top row represents the source language. The bottom row is the target language, and the arrows in between are the translations that happen in the compiler. So when I think about Elixir and Elm from a programming language perspective, I see two approaches. Elm takes the approach of using a small language to tame the complexity of a larger language. And at the end of the day, Elm uses a small subset of features that are allowed by JavaScript. And the trade-off that it proposes is that the restrictions enforced by this particular subset help you create reliable web applications. And a phrase that I've come to really like is that Elm makes it easier to fall into the pit of success. So it's essentially there are fewer ways to shoot yourself in the foot. So by default, you're likely to end up with architecture that people might deem better. I guess that's ideal. Anyway, Elixir, on the other hand, has a larger surface area than its target language. And I listened to a couple of interviews that the Elixir creator did. And the goal, as I'm kind of summarizing what the creator said, is that Elixir aims to bring better ergonomics to the Erlang ecosystem. And so they saw some things about Erlang that they really liked, and they saw some other things that they didn't love so much, and so they created this language to bridge the gap, essentially. And so Elixir allows you to access, it allows you to write code in a way that you could have written it if you were just using Erlang, but it would have been really impractical for you to do. So the names that I'm calling these paradigms enforce restriction on the Elm side, and just to focus on ergonomics in the Elixir example. And this is kind of my conclusion when I think about back to what I asked myself, what the programming language was in essence. And I think the semantics of the programming language, so how it feels and works when you're writing in that language, is largely due to the decisions that the creators made when they were thinking through these two lenses. So what restrictions are we going to enforce, and how do we talk about the ergonomics of the language? And so the observation that inspired this particular talk for me is that I found myself thinking more and more in terms of these two lenses when I'm programming in my normal work environment. So I work at HubTran, and HubTran is a productivity suite, and we automate back office paperwork processes for logistics companies. This is how it looks on the outside, but this is how it looks on the inside. And if you can't read it in the back, I'll read it out loud. It says div, 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 div. And then the important stuff that this function actually does is the blue stuff that's way nested and not at all obvious when this is not manually syntax highlighted for presentation. And so all of these divs and classes are kind of part of the magical layout that's happening here. And I call it magical because it's not entirely obvious when you're just reading this 6 div class combo how this is going to render on the screen unless you go and look at the CSS definitions. Even then, you might not be able to tell. So the classes include things like document browser, container, and main image. And they're not a huge help to us when we're actually working with this function in terms of getting a sense of layout. And so I wrote this code, and it's because I was translating some of the React code that we had into Elm code, and I used an online HTML to Elm converter so that I could make it look 100% like what the old React version was, because I didn't want to create any accidental UI bugs. And I think that that's a fine approach for that kind of use case. But I also think there's some problems in this code from an understandability perspective. And I think that one way to state the problem is that the language that we're using in this file, the vocabulary that we're using in this file, doesn't match the language we kind of want to be thinking about when we're coding our layout in our view. And the language that we're using here is basically the language of HTML and CSS. And so one way that we're approaching a solution at HubTran is that we started to create a UI module. And so instead of using HTML to code our views directly, we made our own type called UI. And this is the module definition line in Elm. And so we're exposing the UI type, and we're exposing a way to take a UI type and turn it into HTML. And so the programmers, when they're coding their views, will build up their view in terms of UI, the UI type here, and then use the toHTML function at the end. So they're not thinking about HTML until they absolutely need to render it to the page. And the language that we're exposing here is intended to make a little more sense for the UIs that we're trying to create at HubTran. And so we have some layout primitives like stacks and rows and columns. And then we have values for spacing. So there are only 3 levels of spacing generally. So in normal usage, you won't find parts of the page that are spaced inconsistently as long as you're using values from this module. And then we have functions for getting the actual content onto the page. And in total, we kind of exposed 40 base expressions in this UI module so far. And the number I'm going to use for comparison is the number of element types that the HTML exposes, which is 90. And the trade-off we're proposing is that the programmers that are using, at our company that are using our UI module will have consistent layout and styling, and that we can enforce semantic markup. So for instance, we don't have any clickable divs. If you want it to be clickable, you can use a button. And that just helps people fall into the pit of success more often because it's trickier to make something that will look bad. And so I think this is an example of a programming language, essentially. So the programmers, when they're creating their views, will use one language, and that language, that vocabulary, is the vocabulary of this UI module that I showed you. And then the UI module later is responsible for generating the target language, which is HTML and CSS in our case. And so this idea is called a design system. We didn't invent it, But a design system is an example of enforcing restrictions, not at a language level, but usually at a library level or a module level, or with specific functions. And so your programmers don't need to make decisions about HTML and CSS. Instead, they make decisions in terms of the system that you define. And hopefully, the system exposes a language that's smaller than the language of HTML and CSS. And so this is exactly how programming language designers think. And when you make a design system, you're making a programming language, so it can be helpful explicitly in terms of expressions. So since the goal of our UI module at HubTran is to enforce restrictions, so to provide a smaller language, if we ever get to a point where we see this number kind of nudging up against 90 and then ever overtaking 90, then it's no longer a compelling system because now we're forcing programmers to make more decisions than they might have otherwise had to if they were using the primitives underneath. So the moral of the story is just like programming language design, module design comes down to scrutinizing the expressions that you allow. There's also a pretty big caveat, which is that calling HTML a 90 expression language is pretty misleading because I just counted HTML nodes. I didn't count CSS layout pages. But I needed a number to put on the slide, so I chose my but I think the real number is way bigger. So that's kind of the way I'm thinking about and illustrating enforced restrictions. So we're going to talk a little bit about ergonomics. And for that, introducing where I also work, Trainer Vision. So I end up working in the mornings for HubTran and in the afternoons on my own product called Trainer Vision. It's a productivity tool for personal trainers to help to hear some of the work they do after hours to set up clients and sessions. This is what it looks like. And this is what it looks like inside. One of the things one of the ideas I'm trying out is an idempotent schema for our database. And so the idea is that in place of migrations for now, we just have a SQL file that has a lot of instructions with if not exists so that you can run the SQL file in its entirety when you want to change the schema. So the interesting and challenging part about this approach is that you can't add if not exists to anything in SQL. So you can't add it to tables, and you can't add it to columns. But for instance, you can't add it to triggers. And triggers are hooks that let you listen to events that are happening in your database and just run code whenever those happen. So this is a trigger that I wished that I could write. Actually, this is how I did write it. And I wanted to make a particular column in this database immutable. So anytime you try to change it before the update, so before it actually writes that change, it will do this check to make sure that the value hasn't changed. And if it has changed, it'll raise an error. But this is not idempotent because it will try to create the trigger every time because there's no if not exists. And it's a SQL syntax error if you try to add if not exists. And so Stack Overflow suggests that you drop it first. And for some reason, dropping a trigger does have an if exists check. But if you drop it and then you create it, but the creation fails, then the old one is no longer there. So there's kind of no guarantee of transactionality. And so what you would want to do typically is wrap it in a transaction. I didn't want to do that here because this to me is it was in my personal preferences, this was an acceptable level of SQL to kind of have to define what I really cared about, which was the schema and what I'm storing. But the 10 lines I showed you before was too much incidental complexity that I didn't want to put in my data definitions. And so my solution was to put it in a function and call that function, which is hopefully not at all impressive. The problem that I was trying to solve was immutability, and so there's no language here in the data definition about triggers or transactions. Instead, we're using a name that's more specific to the context that we care about, which is immutability. So, like I said, it's hopefully not an impressive change. It's called extracting a function, and but it addresses kind of a sentiment that I've come across. I've said it myself, which is that I don't like language X because language X doesn't have feature Y that I like. And I think that nowadays I just find I'm thinking about, I'm making this case less and less frequently because what you could do is think about what building blocks does the language expose, and do those building blocks allow me to make a mini language inside of the programming language that deals with the things that I do care about. So SQL didn't provide affordances to, in this case, deal with immutability, but it provided affordances for me to create a little mini language inside of SQL that does deal with immutability. So looking back, the building blocks that programming languages talk about are expressions. And Elm's approach is to enforce a smaller language to tame the complexity of a larger language, helping people to fall into the pit of success that they might not have otherwise have discovered if they were using the larger language directly. And the Elixir approach prioritizes ergonomics. So it adds features to the target language to give the programmers a nicer experience for modeling their domain. And so these kind of lenses are what I'm calling a programming language design pattern. So when you're creating modules and classes and libraries, thinking in terms of building blocks or expressions, and then thinking in terms about the number of expressions that you're exposing in total, how those expressions can combine with each other, and help your users who are other programmers to fall into a bit of success. And thinking about how users can create their own expressions that better suit their domain, given the primitives that you're exposing with your functions, modules, and classes. So I talk mostly about these as distinct for illustration purposes, but they're not mutually exclusive. And so Elm and Elixir are good examples at a high level because we can kind of pretend that these ideas are mutually exclusive. But a really fun way to think about both of these ideas at once coming together is this idea of zero cost abstraction, which is a phrase that the Rust community throws out a lot. And the idea is that if someone is using your enforced restriction of a language, it should also be very ergonomic for them to use. And in certain cases, perhaps they should be able to peel back the parts in which you've enforced so that they can dig down into the layer of primitives one level underneath and create their own abstractions that can work inside of your language. And so without votes is the online name of someone, and I don't know their real name, but if you go to the slides, and this is a link, and they have a really good blog post explaining this idea of zero cost abstractions. Another way to talk about these ideas I'm talking about is to call them embedded DSLs. It's a bit jargony, but the idea is it's just a formal kind of way to talk about a language that is not actually a maybe full programming language. It's embedded inside of another language. So it's just functions, classes, and modules, or a library inside of another language. But when you use it, it feels like its own language, almost like a gem file or a Ruby routes file, or sorry, a Rails config file for routes. Feels like its own language, but it's just pure Ruby that they've exposed some nice functions to make it a bit more ergonomic. This link, pointfree.co, is a link to an episode of this online video series where these two developers are using Swift to teach functional programming ideas. And they're kind of asking the question in this episode, why do we use both Ruby and ERB for our web servers? What if we just, they're using a whole different language for templating, embedded that building up of HTML inside of Ruby and created an embedded DSL instead of a whole separate language. And so they talk about some trade-offs in that episode. I think it's free. You pay for the whole series, but they release random episodes free, and that's a really good one, I think. And then this is an Hayflight blog post. This is by Javier Garcia. It came out pretty recently. And if you're building an app in terms of domain primitives that you've defined, and it's kind of like working in a mini programming language, and you get some really nice readability benefits, and that's what this blog post is all about. So that's it for me, and I think Nicole said to take questions if there are any. Alrighty. Yes.